Well, hello guys. This is our first video for nuclear science in Nuke 118, and we have to go over a few items so you won't get behind in class. So I need you to turn to your nuclear science chapter 2. We're going to talk about mass defect, binding energy, all the different energies within the atom that we haven't explored in the past. Probably haven't even explored those in your basic chemistry or physics class. So it's going to be a little bit new. In addition to that, we're going to have some properties that are going to kind of mess up what you've already been taught. Anyhow, we have, if you've gotten your nuclear science chapter 2, first you need to move down to the objectives. As you remember, all the objectives is what you're going to be responsible for on the exam. So you need to move down to the objectives, and let's talk about the first couple of objectives. Number one, you got to have electrostatic force, nuclear force, and what are the roles of the neutrons and stability regarding the stability of the nucleus. Now, I don't know if you remember, but electrostatic force is the forces that you had probably already studied in your chemistry class, and those are the ones that have the positive, negative is positive and negative attract, negative and negative repel, positive and positive repel. However, we're going to be learning something new, which is called the nuclear force, and that is going to have a whole different set of rules based on the distance in which the proton and neutron are from each other. The nuclear force has nothing to do with the electrons. I want you to make sure you know that. Nothing to do with electrons. The nuclear force has everything to do with just the protons and neutrons in the nucleus only. Then after that, we're going to talk about a little bit about binding energy. What is binding energy? What is binding energy per nucleon? First, you need to look up the definition of nucleon. Make sure you know what a nucleon is. I'm just going to give you a heads up. Nucleon is one of the subatomic particles in the atom. So a nucleon could be a proton and or a neutron. So that's a nucleon. The binding energy is the energy that holds those two together. So binding energy per nucleon. Then we have fission, mass defect. That's going to be an interesting topic right there. Mass defect. I'm going to mess you up on your past knowledge on mass defect. You're just going to have to press the I believe button on that one. And then mass equivalence, mass energy equivalence, and then finally down to nuclear stability. Then we're going to talk about the purpose of radioactive decay and the 4 basic types of radiation, which you should already know that. If not, we're going to go over those again: mass, size, electrical charge, and so on. So let's move on forward. Those are the objectives of chapter 2. We're going to kind of make this a little bit short and fast and quick so I don't bore you to death. I understand that. That could be a problem. First thing I want to talk about, if you go to what page is this? Page 1 of chapter 2. First starts talking about electrostatic versus your nuclear forces. I have a whole new set of rules for the electrostatic forces versus the nuclear forces. If you remember in algebra, when you were first learning algebra, did your instructor put on the board positive and positive equals positive, and negative times negative equals positive, and then negative times positive equals negative? Well, in this particular case, we have the rules of 2 electrons repel each other. They have both negative charges, which are located right over here. And then you have the 2 protons, and that they're positive charges, and they repel each other also. If you have a negative and positive, they attract. But we have a new set of rules, which are called nuclear forces. And you need to look at these new set of rules that are located right here on this figure 2-1. And the new set of rules is that the 2 protons, positive and positive, attract when they are in close proximity within the nuclear atom. In addition, we have the neutrons, and the neutrons attract. And then we have protons and neutrons attract. Now I want you to make sure that you understand that this set of rules in figure 2-1 only apply to close proximity within the nucleus only. And those are called the nuclear forces. As you can see right here, this attractive force is called the nuclear force. They are much stronger, as it states here, than the electrostatic, which are these located right here, the negative and negative and positive. Much stronger because that what actually holds the atom together. Now, the purpose of knowing about nuclear forces is that because we have to break up or fission the atom in radiation so that we can pull or extract the energy out of the nucleus itself so that we can heat our water in a nuclear power plant. So it's going to be very interesting. I want you to take a look at example 2-1. 2-1, nuclear force is stronger over short distances and is stronger than electrostatic forces at that same distance. So that's the answer to 2-1. Nuclear forces are stronger over short distances. When we're talking short, we're talking very, very small short. And short distances within the atom itself. And then they become stronger than the electrostatic forces at that particular distance. Now there is a certain distance in which the protons and neutrons will escape from each other, and when that happens, then the nuclear forces do not apply any longer, and then we have only electrostatic forces. Alright, let's keep on going. Here's a nice little photograph, figure 2-2, which gives an example of the nuclear forces and the boundary in which those nuclear forces apply. On this particular case, the boundary is very small and short. In that nuclear force boundary, we have the nuclear force rules, which means the proton and proton attract each other, neutron, proton, and then neutron, neutron, just like I spoke about earlier. After you pass, or if a proton or neutron passes outside of that nuclear force boundary, then the nuclear forces disappear, and then the electrostatic forces prevail. So after a proton passes outside the nuclear boundary, then it's going to start repelling the other protons. That is one of the reasons, or one of the characteristics of fusion of an atom, and that goes into play there. Now I want you to take a look at figure 2-3. 2-3 is talking about your nuclear stability, and normally for smaller atoms, right here, anything 20 and below, usually have a 1-to-1 correspondence between the number of protons versus the number of neutrons. For example, carbon has 6 protons and 6 neutrons, giving it a total atomic mass of 12. Same thing with nitrogen. Nitrogen has 7 protons, 7 neutrons, giving it a total atomic mass of 14. However, as you know, we get further up on the line. Notice the line of stability starts moving to the right. And the reason for that is because it's going to require more neutrons than protons to make the atom stable as we increase the size of the atom itself. So, as we get past this 20, right around 20, then you see the line of stability starting arcing to the right. And that exemplifies the fact that we have more neutrons in the atom than protons, so that the atom will be stable in itself. And this happens for many large atoms. That's how that occurs. So as you can tell, if you look through the chart, as you move along, the number of protons for uranium is approximately 92. So let's find that. There's about 92 protons, which is, excuse me, I was on the wrong spot. 92 protons, and as you can see as we go way over here, the number of neutrons are going to be way over in this distance here. So as you can see, to make a uranium-238 atom stable, we have to have much more neutrons than we have protons to increase the stability. Okay, you think you got that covered? Alright, we'll move right along. So that was the stability, nuclear stability, the neutron to proton ratio chart, figure 2-3. Okay. Alright, then we're going to move on to different types of radiation. What is radiation decay? What is that? Why does it happen? And how do we gain the energy from radiation decay? So let's first look at the definition of what radiation decay is. Here we go right there. Radiation decay is the process by which an unstable nucleus spontaneously transmutes from one form and element to reach a more stable state. So it's pretty easy to understand. If we have a fission of an atom, for example, uranium-235 or 238, it's going to continue to fission until it comes down and moves to a state of stability. In that state of stability, then it will no longer decay, and therefore no more radiation will be emitted from the atom itself. So that's what it's talking about there, that it spontaneously transmutes from one element to another to reach a more stable state. The radioactive decay process is a normal process, and you can find that in many natural atoms on the planet, and it does occur naturally with uranium in the state, even in the stable state. Let's talk about different type of particles that are emitted in different types of radiation. So we have four basic ones. We're going to start with the alpha. Let's look at here. We have four basic. We'll get that. There we go. Alpha particles, beta particles, gamma rays, and neutrons. So we need to know those four: alpha particles, beta particles, gamma rays, and neutrons. What's great about alpha particles is alpha particles are much larger if you want to compare it to the other types of radiation. The alpha particle is a much larger particle, and it consists of two protons and two neutrons. And from your periodic chart, if you remember correctly, 2 protons, 2 neutrons, that is actually a helium nucleus. Now it's not a helium atom, because if you had a helium atom, you would have to include its 2 electrons also, but this is not the case. It has just the alpha particle is the 2 protons and 2 neutrons. It is considered large in the atomic world and also in radiation. So a helium nucleus of that size can be stopped with as small as a single piece of paper, which is listed right here. So alpha particles not necessarily can cause a lot of damage, especially in a nuclear plant if you're wearing your protective clothing, your goggles, and so forth. The alpha particle is not going to be able to penetrate you and cause cellular damage. The alpha particle will be stopped by the dead layer of your skin. So even if you have your skin exposed and you're in an area where there's alpha particles being emitted, your dead layer of your skin will actually stop an alpha particle from penetrating the rest of your body. However, you need to be very careful about your eyes, and I can't stress that enough. You got to watch your eyes, and because the alpha particle can get into the fluid in the water in your eyes and cause damage in your eyes. So always be sure to wear your safety goggles. Make sure you always have those on in any situation when you're at the nuclear plant, because I don't want you to be blind, and that's one thing that can happen. Let's talk about the beta particle. Beta particle is a positively, now this is kind of strange, a positive and or a negative charged, and we consider an electron. It's got the same mass that of an electron. Now you think from your chemistry and physics that you've been taught that all electrons have a negative charge to them, and that's correct. They do, but in the particular case in this radiation that's emitted, you can have a particle that is a positively charged quote-unquote electron, and we'll learn that more when we go into what happens when a proton actually breaks into 2 pieces, and one of those is going to be a neutron and the other piece is going to be an electron, or what's considered a positron. Now I want you to take a look down here. We're going to only spend a lot of time speaking about the electron, the beta minus, which is the negative beta particle listed right here. And as you can see, also it is found based on the text. It says it's commonly found fission products created in the fission of a fuel commercial reactors. So we will be subject to the electron, the beta particle from radiation, and so we need to take a look at what stops a beta particle. And if you come back up here, notice that a thin sheet of metal and most of your safety glasses will stop beta particles. It says nothing about dead layer of your skin. So if you do have skin exposed and you're in a location where there is beta particle emission due to radiation, that it can penetrate your skin and go a little bit deeper down into the lower epidermis of your skin layer. So beta particles not as bad as some of the others, but not as easily contained as the alpha. So a thin sheet of metal. You got to remember that nuclear power plant, we have a lot of metal, we have a lot of shielding. So a lot of the beta particle is not necessarily going to be detrimental to you. However, if you are exposed without safety glasses or without some kind of protective clothing, you can be subject to the beta particle. Let's move on. Gamma rays. Now gamma rays is an electromagnetic energy. It's not a particle. The other two were particles. Gamma ray is not. It's electromagnetic energy. And this is the more dangerous type of radiation that occurs. The gamma rays can penetrate the skin. They can actually go through large bioshields or sometimes through bioshields, and they can cause detriment and cellular damage within the skin. Think about gamma rays, they pretty much just pass right straight through you. The gamma rays are, if you look at what can stop a gamma ray on your text, the distance the gamma ray travels, okay, distance through a few inches of metal and a couple of feet of concrete. See if I can get that highlighted properly. Through a couple of feet of concrete will stop a gamma ray. So a gamma ray will actually go through your body, and if it does go through your body, that particular type of radiation can cause harm to your cellular structures and cause mutations and so forth. So we want to stay behind our bioshields, which are made of lead and thick walls of concrete, if we're in the location where gamma rays are going to be located. Remember, HP is your friend, and HP is going to be watching out for you. They're going to be letting you know where they have subject to gamma rays when you're working in a radiation controlled area. Now the last one we want to talk about is neutrons. And neutrons, even though this is what we desire in a nuclear plant, we desire a radiation of neutrons because during the fission process the extra neutrons are going to continue the fission process so we can maintain or create or gain our energy so we can heat the water and actually cause to make steam. But the thing about the neutron is that a neutron, it can be stopped by a few feet of water. Water is a good what's called moderator, which means it moderates the speed and the energy of the neutron. And what would happen is the neutron gets released during the fission process of uranium-238 and 235, and when that happens, the neutrons actually start bombarding other atoms in its path, and then from that bombardment it constantly starts losing energy, and as it loses energy it finally gets incorporated into another material's atom. And when that case, it may have enough energy to actually cause another fission process. But what's really good about the neutron is that it can be stopped, as you can see right here, by approximately a foot of water, and also by concrete and lead. Now, that one thing that's very, very important that you need to remember is that the neutrons are the parts of the fission process that we are actually concerned with in our nuclear fission and creating steam. The neutrons are extremely dangerous to cellular biology. That would be if you were in contact or close contact to any fission process creating neutrons, it can leave you very well scarred and or radiation sickness. But as you recall, in the nuclear power plant, we always keep the fuel underwater. And the reason for that, keeping it underwater, is specifically to stop the neutrons and maintain them as a moderator. Also, while we're talking about neutrons and moderation, there's also another chemical that we use at the power plant, which is called boron. Boron's a nuclear poison, and that nuclear poison meaning it can actually absorb neutrons and therefore reduce the fission process by absorbing more neutrons. So at the nuclear power plant, we not only use water to maintain or control the amount of neutrons, but we also use boron. We inject boron into the RCS, which is the radiation control, reactor coolant system, and in the RCS we inject boric acid, and the boric acid can actually absorb neutrons, excess number of neutrons, so that we can maintain and control the reaction that's going on in the reactor, and therefore not cause it to get out of sight and turn into what we all know, a nuclear disaster like Chernobyl. Alright, that's the first one. We're going to stop there and then we'll move on right after that.